the world. Now, back to business. Large sample confidence interval. We started on Monday, interval estimator, and we want to continue because we're talking about interval estimator. Depending on the nature of the sample size could be small, sample size could be large. And, when sample size is large, okay, then how can we actually compute our interval estimator? And that is the reason why today's topic is actually going to be the interval estimator, or the confidence interval that we actually put in place, using large sample. Does that make sense? Which means using large sample so that that will enable us to use central limit theorem, and that will facilitate normality. And when that facilitates normality, I will be able to use this call. Does that make sense? Okay, now we actually want to recall, want to see what we've done here. We want to recall, the whole idea starts from the fact that we actually want to figure out the value of a parameter. Okay, we want to figure out the value of a parameter. If you want to figure out the values of a parameter, theta, and we want to seek redress taking sample, then we should be ready to use what I call an estimator. The estimator is theta cap. Okay, and let me tell you this situation where the sample size is large, then we expect the probability distribution of an estimator theta cap to be approximately normal by central limit theorem. And that was why you see theta cap is approximately, follow normal distribution with the mean of theta and the variance sigma squared theta cap. Now, if that happened to estimator, okay, if that happened to estimator, then this is also going to happen. There's always, we're also going to have an approximate standard normal distribution. Okay, when you attain an approximate normal distribution, an approximate normal distribution will also lead to approximate standard normal distribution. And that was why I said normality facilitates standardization and z-score. Now we're actually going to have z, which is going to be the difference between the estimator and the true value of the parameter divided by the standard deviation of that. Where do I get the standard deviation of that? For finding square root of that variance. Okay, and that C is actually going to be approximately, it's going to follow standard normal distribution with a mean of 0 and the standard deviation of 1. And if that happens, do you know the implication of that? The implication of this guy now. It's actually going to resurface, putting into consideration some common estimators that I showed you the other time. Okay, the other time I actually walk you through some common estimator that we use in statistics, where we actually want to this is our target parameter. We may want to figure out the mean, which is likely going to be the average household income in a particular country, or we want to figure out the P, which is a proportion, the true proportion. Maybe we're trying to say the proportion of those who are living below certain poverty threshold, and me1 minus me2, maybe we actually want to compare means in two populations. Maybe you want to compare the standard of living in two countries or stuff like that. And P1 minus P2, maybe you actually want to compare the proportion of those who actually, maybe you want to compare infection rates in two groups. The first group actually get vaccinated. The second group did not receive any vaccine, and you actually want to know the proportion of infection, okay, in the two groups. Okay, so if you want to do that, of course, I told you the other time, we cannot study everyone in the target population. Because of that, we are not going to have a way to exactly compute the population parameter value. We're always going to take a sample, right? And for us to be able to use the idea of standardization and z-score, then the sample that we choose has to be sufficiently large. And at the end of the day, when that happens, the corresponding estimator, okay, if you take a look at this guy now, okay, so when you take a look at all of that, they are all estimators. They're all going to follow normal distribution, okay? And their means, the means of that is actually going to be the target parameter value. And at the same time, we're also going to have, when I put a square, okay, on the square root, I'm going to be talking about variance. If I don't put a square, I'm going to be talking about standard deviation. So I need you to take a look at all of that. I told you the other time, statistics is like a story that goes on and on and on. Now, let me tell you this. A situation where you are working on two groups. Maybe you are comparing the means in two groups, or you are comparing proportion in two groups. Assumptions is that the two groups are independent. Does that make sense? They are independent. I just needed to take note of that. Now, I want to move right now. We believe working with the last sample. So working with the last sample, we actually facilitate the use of z-score, and the focus is actually going to be on the standard normal random variable. Now, I said for standard normal distribution, for any alpha lies in 0, 1, I'm actually going to call alpha here the level of significance. That we also call the level of statistical error, okay, which is the maximum probability of committing type 1 error. Okay, now we actually want to find what is the probability, okay, of a z-score. The probability of a z-score, take a look at that. That guy means the probability of a z-score, because what you have in the middle, it's actually a random variable that follow normal distribution with the mean 0 and the variance 1 or standard deviation 1. We're actually referring to z-score. So the probability of a z-score lying between this and that, that and that. You remember the other time when we were working with the Chebyshev inequality? When we were working with the Chebyshev inequality, we said the probability of the absolute value of a theta cap minus theta, okay, now less or equal to k. This is going to be the standard deviation of that. Maybe I'm assuming this guy is an unbiased estimator. The probability of that will be greater or equal to 1 minus 1 over k squared. Now, when you take a look at this guy now, okay, that is actually going to be a constant, okay, which is like k number of standard deviation. Okay, now when I say k number of standard deviation, you remember what we did the other time, working with the error of estimation, where we were creating a bound. Okay, when k equal to 1, it means we want to create one standard deviation error bound. When k equal to 2, we want to create 2 standard error bound. But this time around, we don't want to assume k to be a value, but we want to figure it out using the information we got. The other time, I'm going to repeat this again. The other time when we're dealing with the error of estimation, we assume value for k. Okay? Where I said, get this within 2 error bound. That means I'm saying k equal to 2. But this time around, we're not going to assume that. But we believe that the probability of z lie between, if you take a look at that picture, if you take a look at this now, that's a typical normal curve. Okay, typical normal curve. You can see the center, and of course, you see the in the entire space. Okay, you see alpha can be partitioned into 2 equal parts. That's going to be on the extreme, okay, on the extreme. Okay, so alpha over that, sorry, alpha over 2 to the left, I'm actually going to call that a negative z. Alpha over 2 then to the right, I'm actually going to call that z alpha over 2. What are we looking for? What is the probability that something is going to be greater than this, okay, and less than that? Then, which means we're actually interested in the middle. Does that make sense? It means we are interested in the middle. And if alpha over 2 plus alpha over 2 actually give alpha, then the middle one will be 1 minus alpha. Because the total area under a curve must be equal to 1. So which means alpha plus 1 minus alpha will be equal to 1. And that is the reason why we equate that to confidence coefficient 1 minus alpha. Does that make sense? Now, if you have that guy now, or equivalent, I can just find the probability of that greater or equal to that. And the probability of that, of the random variable z, greater or equal to that will be equal to alpha over 2. And let me tell you this, we can actually, the z-score can be found using the normal table, okay? And that is, one of the reasons why we want estimator to the distribution of estimator to converge to normal is for simplicity, for us to be able to make use of a z-score, okay? For us to be able to make use of a table. Okay, now, moving forward now. Now, moving forward now, let's take a look at this question. For 4 common point estimator above, the 4 common estimator that I showed you the other time, okay, how can we construct a confidence interval of the confidence coefficient? Whenever you want to construct a confidence interval, we always actually need to have a confidence coefficient. Does that make sense? The confidence coefficient is more or less going to be what level of confidence do you want to tolerate? Do I want to tolerate 95% level or something? Now, I want to show you right now. How do we construct? Let me tell you this. If the point is for interval estimator to do a great job, then the point estimator has to do a great job. Okay? Now, I need you to take a look at this now. I want to walk you through how do we derive a formula for interval estimator for a point estimator mean. You've come across those formula before, but how do we come about it? Then I want to put it to you. We come about it, putting into consideration convergence of distribution to standard normal. Take a look at this guy. Give me 1 second. If you take a look at this guy, before we can have an approximate distribution, to standard normal, then we already have a sufficiently large sample, central limit theorem, old, at least story, sample size story, and the distribution of theta cap already follow normal. Okay, now I need you to pay attention now, but what do we want to do? We actually want to find the probability of a z-score. You remember the picture, the normal curve that I showed you the other time. We want to figure out the probability of a z-score. That guy in the middle is a z-score, right? That's a z, right? We want to figure out the probability of that line between the negative z alpha over 2 and z alpha over 2. Okay, that's what I want to do. And that is approximately 1 minus alpha. The 1 minus alpha is a confidence coefficient. Now, we need to go algebraic now. We need to simplify. I actually want theta in the middle. I want the parameter in the middle. Why do I want parameter in the middle? Because what I'm trying to tell the world is that the true value of a parameter lies in the interval. And that is what I want parameter theta in the middle. Okay, now what I'm going to do, I'm going to multiply this by the standard deviation. Then I'm actually going to transfer the other, then at the end of the day, take a look at what I have. Any question? That's mathematics. Any question? Now, when you have this guy now, what are you telling the world? You are telling the world the lower bound is this guy here. The upper bound is this guy here. Now, instead of you to assume a value for Z, just like what we did in the last lecture, where we said we did 2 error bound, 3 error bound, then we're actually going to use our data to figure out what the values of Z is going to be. Does that make sense? Do you all see the connection now between what we're doing now and what we did the other time when we talk about error of estimation? In the error of estimation, we actually assume a value for K. Oh, 2 standard deviation, 2 error bound, 3 error bound, but we don't want to do that. That may not be realistic. Can't we have a way to, optimally compute that value from the data set? Okay, and of course the good news, yes, we can do that. We can do that because the central limit theorem will facilitate normality, and normality facilitates the use of the z-score. And that is the reason why, at the end of the day, take a look at this guy now. When you take a look at that guy now, this is going to be the lower bound, and this is going to be the upper bound. And let me tell you this, after the minus, what appear after the minus and what appear after the plus, okay, they are all the same. And that is what we call the margin of error. Margin of error. The margin of error, the reason why we cannot rely on only point estimator, the point estimator does not put into consideration margin of error. But the interval estimator put into consideration error to the right, error to the left, and we're actually going to have opportunity to be able to know how the population review what we already observe in the sample. Okay, so take a look at that. Okay, now I'm actually going to say in the remarks, this is what we call a large sample interval. That is what we call a large sample interval. Now, you know what I want to do now? If that is a large sample interval to all the 4 common point estimator, okay, to all the 4 common points, if I have this parameter, then what you see on the other side is actually the last sample interval estimator. Take a look at that. Okay, can you see that? You can now use that. The only thing is just like estimator minus the margin of error. If I'm talking about mean, the estimator is y bar. What is the variance of y bar? Sigma square over n. What is the standard deviation? Find the square root. That is sigma over root n. If you take a look at proportion, you remember the other time when y follow Bernoulli distribution, what is the variance? P into 1 minus P. What is the variance of a P cap? A P cap is going to be y bar. The variance of a P cap is going to be P into 1 minus P divided by n. What is the standard deviation? That's why you have a square root. So, whatever you have before the Z, that is standard error. When you multiply the Z by the standard error, that gives you the margin of error. So there's a difference between a standard error and the margin of error. The standard error is the square root of the variance of the estimator. And why are we using standard? Why are we using standard error or standard deviation? We are assuming the estimator are unbiased. Does that make sense? And so I present to you, this is a formula in the lower statistics course, where you actually want to compute an interval estimation for mean, You want to compute an interval estimation for proportion for one population, or you want to do that for two population, this is how we arrive at the formula. Is there any question here? This is what we call large sample before we can use anyone that has Z in then the sample size has to be sufficiently large. Does that make sense? Okay. Now, let me tell you this. I want us to try something now. If the level of confidence is 95%, which means 1 minus alpha is 95%, alpha will be 5%, right? Okay. If you plug in 0.05 into alpha and you check in the table, in the Z table, that will give you 1.96. For those of you who use R, if you do a P norm, okay, a P norm, or sorry, a Q norm, rather, Q norm, because you want to get a Z score. If you do a Q norm of 1 minus alpha over 2, for instance, your alpha is going to be 5%, is 0.05 for 95%. That will give you 1.96. Oh, 1.96. 1.96 is approximately 2 standard error bounds. You remember the other time when we just assume a value for K, okay? When we are using 2, we are very close to, the Z-score of 1.96. Does that make sense? Okay. Now, that is what I mean. Now, I want us to go into an example now. See, go ahead. Okay, so you know, in mathematics, we don't just do addition or subtraction. Uh, you know, we can have mu1, we can have mu1 minus mu2, we can have mu1 plus mu2, but we use minus when we're looking at the difference. But situation where we're using plus is maybe we want to look at everything together. Oh, we got a company, we are producing 2 different items, right? The first item is a random variable, okay? Random variable in terms of the number that we produce. The second item is also random variable, okay? It varies, what we produce varies. And I actually want to know the total production. The total production is also going to be a random variable because the component of each of that vary, okay? Then we can have mu1 plus mu2 in that situation. But that situation, we're only interested in figuring out the probability. Maybe want to answer a question about totality, not the difference. But the common point estimator is only there, they are only talking about, the two of them is only talking about, okay, let's compare means in two population. Is there any different? Then we're going to go by minus, or let's compare the proportions. We're also going to go by minus, but let me tell you, can we also compare variances? Yes. We can compare variability in two systems, but we're not going to use minus for variance. We're still going to get it. We're going to use a ratio. Okay, whether minus or a ratio, they perform the same function. They are for comparative analysis. I've answered your question now. Yeah, go ahead. Okay. I know that there are some that are standard, but what if in a situation, the reason why you need to know how to check from the table, what if I did not ask you the special one? I know the special one is going to be 90%, 95, 99. What if I ask you 96? And that is the reason why you need to be able to know how to compute that. Does that make sense? Even though we got some special one, but examiner can decide to, ask you 97% confidence. That is not a special one. So you need to be able to know how to make use of the table. You see what? Yeah, the table will take care of whatever level of significance. See, take a look at this. Give me 1 second. Take a look at this. If I want to use R now, I only need to know my alpha. If the confidence level is 97, alpha will be 3%. This is going to be 0.03 here. So any level of significance given or any confidence level given, we can determine the alpha because the level of significance and the level of confidence are mutually exclusive. Does that mean that they complement each other? Go ahead. Of course, in the exam, yeah. Even me, I may not be able to write the exam without the Z table. What of if they just give me 97 or 94 or 82% confidence, Yeah, there's going to be provision for that. Yeah. Can you say that again? Oh, can I explain the margin of error? Do you mean the meaning? Oh, okay. You know, when you talk, let me first start from standard error. Margin of error is when you multiply the quantifier Z by the standard error. That is margin of error. Now, but the standard error is just telling you how the estimator deviates from the average of the estimator. Does that make sense? So you look at the square root of that. That is what we call the standard error. But the margin of error, we not only consider the standard error, but also going to consider the quantifier. The other time we just say, okay, like like within what standard deviation from the mean. There's a deviation. Okay, now we have to consider that, and that is what we want to figure out using the Z. Does that make sense? Okay. Now take a look at this question here. The shopping times of n equal to 64 randomly selected customers at a local supermarket, okay, were recorded. The average and variance of the 64 shopping times were 33 minutes and 256 minutes squared. Anytime they give you, talking about variance, the unit variance is in square units. Okay, estimate meal. You want to estimate meal, the true average shopping time per customer with a confidence coefficient of 1 minus alpha equal to that. Now, let me tell you this. You need to be able to look at the sample size to see whether the central limit theorem applies. Now, the sample size here is 64, right? And the threshold for the central limit theorem is actually 30, right? Okay, so because of that, I'm going to say the central limit theorem applies. Now, the theta here is mu, true value of the parameter, and the estimator for the mu is going to be y bar, which is theta cap equal to y bar. Okay, now by central limit theorem, how do I know the distribution of the theta cap? Y bar will follow normal distribution because of the sample size of 64. Does that make sense? Okay, now I will be able to use a central limit theorem. Okay, now then I will be able to use the formula for the last sample size that I showed you earlier. Okay, so which is going to be this guy here. The guy, give me 1 second. Do you see that? This guy and the guy, I showed you the other time. That is what we're going to use. So this is for large sample confidence interval. The large, you look at the sample size. Okay. Now, all you just need to do, even though in this formula, you can see sigma, right? The sigma is a population standard deviation. You are not given, but you can actually plug in the sample the sample estimate, because we've proven this class the expected value of a sample variance is a population variance. So that's what I'm trying to say here. And at the end of the day, this is what you're going to find. Okay, if you take a look at give me 1 second. I'm actually going to So if you take a look at that guy now, you plug in the value, Then we go to the table to check for Z0 or 0.05, okay, which is we're actually going to have the result multiplied by that, and at the end of the day, okay, if we want to make a conclusion, we're going to say with about 90% confidence, the interval that we enclose mu, which means we believe the true value of parameter will lies between 29.71 and 36.29. Does that make sense? That's what we mean. Now, there's something I actually want you to see here. Okay. There's something I actually want you to see here. Now, for instance, looking at the same question, if we're no longer, if everything stayed the same, okay, if everything stayed the same, and we're no longer using 90% confidence, and we just want to increase the level of confidence, when you increase the confidence level, okay, you're actually going to have a wider confidence interval. Take a look at this. Give me 1 second. If you let me see if I can use this guy here. Should be able to use the guy. Okay, so if you take a look at this guy now, what has changed? Instead of us working with 90%, we work with 95% level of confidence. This is 29.08 to 36.92. That will be more wider compared to 90% confidence level. Now, if everything stayed the same, when you increase the level of confidence, the interval is going to become wider. Does that make sense? Okay, that's what it means. Now, what if in a situation where we're still using the same level of confidence, but what we want to increase is the sample size? What is the effect of sample size? Oh my God. If you go back here, you're actually going to see that sample size can be found in the denominator. The more the sample size, the less the value of the standard error will be small. When the value of standard error is small, oh my God, the margin of error will be small. And when the margin of error is small, then the interval will be narrower. Does that make sense? So what will make an interval to be narrower? And don't forget the other time we said from day one, if I really want to trust my interval estimator, then the range, the interval should be narrower. If you want your interval to be narrower, then you should be ready to take more sample size. And that is exactly what I just talked about here. Okay, as you can see here, we make use of that and compare the two. Okay, I needed to compare this guy, okay, this guy with this guy, okay, compare the two of them. Okay, if you compare the two of them, you're actually going to see that this is narrower because of the fact that there's more sample size is involved. Okay, I'm gonna move right now because of my time. We got the information now. Okay, we got the information now. Okay, now this is the summary. When the level of confidence goes up, of course, the level of significance go down. If I go from 90 to 95 level of confidence, then that means I'm actually going to go from 10 to 5 level of significance. And what happens is this score go up, okay? And what happened to the width? The width of the interval, they also go up. When the sample size increases, go up, the standard error is going to come down because the standard error has sample size in the denominator. And of course, what will happen to the width of the interval is actually going to be narrow. Okay, I just need you to take a look at that. Okay, so the next thing we want to do, I think I provided more example. Okay, so let me see. Okay, now this example is has to do with two populations, and I think the focus is on difference of proportions. Okay, difference of proportions. Let me show you. Okay, you can see what I was talking about the other time, reason why you can't cram. Somebody will ask a question. Here, the level of confidence is 98%. So, so okay, now take a look at this question. Two brands of refrigerators denoted A and B are each guaranteed for 1 year. In a random sample of 50 refrigerators of brand A, 12 were observed to fail before guarantee period ended. An independent random sample of 60 of brand B refrigerator also revealed 12 failures during the guarantee period. Estimate the true difference, okay, proportions between the proportion of failures, okay, during the guarantee period, okay, with confidence coefficient approximately 0.98. Now, of course, we're dealing with a difference of proportion here. And of course, we all know the estimator we're actually going to use. That's going to be pickup 1 minus pickup 2. But you know what? We need to first obtain the pickup 1 and the pickup 2. Now, the pickup 1, the proportion of failure. Proportion of failure is just going to be the ratio of how many fail out of the sample size. 12 over 50 for the first one, 12 over 60 for the second one. And of course, the target parameter theta is actually P1 minus P2. That is the target, right? And we're actually going to make use of an estimator, pickup 1, pickup 2. And because the sample size, choosing the numbers of refrigerator of brand A and B, they are both greater than 30, then the central limit theorem applies. And that was the reason here where I actually, give me 1 second. So that was the reason here where I actually assume that, the difference of the proportion here, the sample proportion here will be approximately normal distribution because the sample size choosing from the two brand of refrigerator, they are each greater than 30. Okay. And of course, the theta here is going to be the mean of this guy, which is P1 minus P2. Then the variance, okay, don't forget we're dealing with proportion, okay, for the two population is actually going to be this guy, and the standard error is just going to be putting a square root, okay. Now, I'm actually going to use last sample interval. Oh my God, you're going to see this guy now, okay. Take a look at this guy now. That is actually the interval estimator for last sample for the difference of proportions. Okay, so what I'm just going to do is just to start plugging in the values. But you know what? I don't know P1, I don't know P2, but I'm going to replace them with pickup 1 and pickup 2 that I know. Okay, so moving forward, okay, you can see that now. Give me 1 second, take a look at that now. Initially, what you have inside the square root, the P1 and the P2 do not have cap. But because of the fact that pcap 1 and pcap 2, they are each unbiased estimator of P1 and P2, then they can actually replace them so that in the entire formula, you're actually going to have a pcap 1 and pcap 2. Now, plugging in the values now, okay, when you plug in the values at the level of when you check the Z, we actually going to have, it's either we have it in this form or we have it in this form. Okay, we can actually have interval estimator in two form. In this form is to tell the world 0.04 is this is actually the difference of the sample proportion, the one I call the point estimate, and the 0.04 as a point estimate could be wrong or right, even when you have done the writing. And this guy now is a margin of error. We consider the margin of error to the left and the margin of error to the right, or we can better see, subtract that from that we got this, add that to that. That is what we have. And how do we now take a decision here? If you want to take a decision, you check, can we have a 0 in the interval? or we don't have zero in the interval. When you have from negative to positive, then there can be zero in the interval. And that was why I said we notice that this confidence interval contains zero. When a confidence interval contains zero, then there is no statistical significant difference. Even though there can be mathematical difference does not translate into statistical difference. Quote me anywhere in the world, because statistical difference, we are talking about statistical significance. We're talking about difference that is very much pronounced, different that cannot be attributed to normal variation. Does that make sense? And that is why, we all know different exists between the two proportions of failures, but the difference that exists is not statistically significant because of the fact that zero can be found in the interval. Because when zero can be found in the interval, the possibilities are okay, no difference. And that was why I said, just a zero value for the difference in proportion is believable, which is possible to happen. So at approximately the 98% confidence level, on the basis of the observed data. So however, the interval also include 0.1. Okay, if you take a look at this interval, there's also possibility of 0.1, which represent another value for that that is also believable. There's so many values in that interval, but let me tell you this: having so many values in the interval, all the values cannot be wrong at the same time. But you know what? When you only focus on a point estimate, it is 50-50. A point estimate could be wrong or right. Imagine you committed a lot of resources to your research only to be let down by poor statistical tool. And that is the reason why in any research paper, we normally consider interval estimate. Is there any question before I go today? Is there any question? Is there any question? Okay, now, lastly, I'm also going to say this. I'll take a look at this. You know, uh, somebody asked me before. I think I see her like 2 minutes. Somebody asked me before, what is the meaning of confidence interval? The confidence interval is just trying to say, when I perform this experiment 100 times, when I say 95% confidence level, it means the true value, when I'm going to get the true value will lies in only 95 of the intervals, approximately. Does that make sense? If you take a look at this, we have 24 intervals here, and the true value is 0.5, and you can see this guy. Oh, wait a minute. Do you see this guy? Oh, let me see if he's gonna. Do you see this guy, right? That guy fall out of which means out of the 24 here, out of the 24 intervals is only 23. Now use your calculator. 23 divided by 24, that should be 95 point something. Okay, but we're trying to say on the long run. Okay, now using 95% confidence interval with that experiment, it's actually done 100 times with 100 intervals. The true value will only lies in the 95 out of them, which means there's also possibility it's not going to lie in 5 out of 100, and which also confirm the fact that model is not the same as reality. Okay, is there any question before I go? Enjoying your Valentine Day. Bye for now, everyone.